This is all about trying to leverage the existing soil health literature for future research to make your literature searches more complete and easier, and also more comprehensive, so it's not just about keywords, but hopefully about causation. Okay, so search is often considered solved. So you can enter in terms into Google Scholar, for example, and get thousands and thousands of results. But here's the problem. It turns out that nitrogen is really important for soil health, so there's a lot of papers. So do you want to sit and read 30,000 papers? Probably not. And even more, these are not guaranteed to be about nitrogen. They just mention nitrogen. On the other hand, there are many domain-specific things you might want to find out that Google can't handle. So for example, I want to know only about cold soils, and I want to say, what does cold soil mean? It's less than 8 degrees Celsius. But Google won't know that, with or without quotes, right? Because it doesn't do this kind of topic modeling. Now, there is a solution to this, which the Soil Health Institute already has. So you can avoid this giant black hole of data and reading all these papers, which is the research landscape tool. And if you haven't looked at this as a researcher, I recommend that you do. I think it's really great. So not only do you have your keyword search that's very similar to what Google can accomplish, but also on the left side there you can see what we call facets, which is basically just filtering the results by certain topics that are broken up into different parts. So different systems, different crops, different temperatures. And that already exists. Soil Health Institute has been working on that, and I think it's already a great tool. But there is a limitation of this, which is that the annotation of this has to be manual, which is very time-consuming, as some of you might see on Friday if you come to our annotation bee and try out the annotation yourself. Okay, so luckily there are tools that already exist that can help us do this annotation automatically with some training materials. We started with materials that were already existing in the research landscape tool. So you can see here, we're getting 51 results. We could pump that up, and this will only become more profitable as there are more papers to look through. Okay, so forgive me for the graph, but this is just to talk about how we approach the problem so that it's not this magical machine learning, artificial intelligence ball. So say you have a lot of papers, and each one of these dots on here is a paper, and they mention the word organic a lot of times, and a lot of other words too. And we want to know, is the paper about soil organic matter or not? So if you look at the means of these two groups, they are different. So this is an important word for this topic, and this is all made up data, but you get the idea. But they overlap, so you can't just draw a line in there. A slightly better model is a linear model, which the researchers here are probably very familiar with. But for this kind of data that is categorical like this, it works a little bit better to do one of these kind of things, a logistic model. And we basically make curves for every one of the words that we see in all these papers, and for all of the 2-word sequences as well. And we tried 3-word sequences and so on. And then we take the ones that seem to be the most important, and we look at those. And that way we can sort of just add up all the scores that are produced by these curves, and that way we can say for each topic, for each paper, is the paper about this? Okay. So you take your articles that you want to annotate, or that already have this annotation information, and ones that you want to annotate as well. And we were lucky enough to have access to Access through the Soil Health Institute's partnership there. And that was very useful because there's a large overlap with the research landscape tools annotations that existed. And we just collect them and convert them to a form we can use. And we do something that we call feature extraction, which is really just counting the words in this case. So it's exactly what I was describing to you before. And we have what we call classifiers, which is what says for each one of these topics, does the paper fall into this topic or not? And we have an independent one for each one of these tags, such as soil organic matter. And then from that, you get your labeled documents. And we're able to then assess what are the most important words and what are the most important words for a given document for it. So the weighting on each one of these features, each one of these words and two-word phrases, you can zoom in here and look. And on this mapping here, green means it's very important for soil organic matter, and the red means it's not as important. So you sort of add up all these words and two-word phrases for the whole paper, and that's how you get your classification. And this is indeed about soil organic matter, and it's a dead giveaway because it says soil organic matter right there, right? Not all the topics are that simple, right? So some of them are more vague, right? But this one is a really good example. So looking at the categories that are on the Research Landscape tool, just to give you an idea, so these words and phrases are important for identifying physical indicators. So anything you're physically measuring about the soil, such as bulk density. And then this is the chemical indicators. So you can see, CO2. Corn is in all of these because corn is really important, I guess. And then similarly for the biological indicators. So microbial biomass, for example, is super important there. Still, carbon dioxide is important, of course. And then we can also measure, given the papers that are already annotated, how accurate are all these classifiers. So there are so many tags that each one of these dots is a separate classifier. So you can see on this graph, basically it's accuracy on the y-axis. So you want it to be high, and you have the number of positive examples in the training set on the x-axis there. So if you look at the trend line there, it's pretty apparent immediately that the more examples you have, the better. And this is not a new thing. This is true of all of these so-called supervised machine learning algorithms. So the more examples you give, the better the machine can tell, right? And it looks from this data like the cap might be at 75% accuracy. So 50% accuracy here is chance, right? So we're doing better than chance. But in fact, if you increase the number of positive examples still more, then you can get more advanced machine learning techniques, which are already available. We just need the data. So how do we get this data? We developed a piece of software. It's available through the internet. So it's nothing, no need to install anything. And you can sign up and annotate papers to your heart's delight. For right now, we have the physical, chemical, and biological indicators, but there are other tags that we could add to this. And it's a pretty simple situation where the machine learning algorithm has already predicted the tags for a given document, and then you just have to sort of edit them and amend them and save your changes. And the more that you do this, the better the algorithms will get. And so the good thing about this is we go through our familiar collecting documents and then classifying them, but now we send our results to you guys, expert annotators, who will then feed back this information to the classifier. In a situation, this setup is often referred to as active learning because you're giving constant feedback to the classifiers. And the best part about this is the classifier is able to tell which documents are the most confusing to it. So it'll show you those documents and you annotate those so you get the maximum benefit out of your annotation. Okay, so we used Annotaurus, and when I say we, I mean Steve Schaefer, used Annotaurus for a couple of hours, annotating a few of these tags. And these arrows indicate the improvement in these tags over the course of those 2 hours. So in the center there is the mean score. So he basically took it from below average or below chance to above chance. The only outlier there is sustained plant and animal life, and the reasons for that are probably obscure, but it's probably just that they need still more training examples for good classification. Okay, so hopefully we can do this with all of the tags, and hopefully we can get much better than 50%, and I hope that all of you will get a chance to help out with that. Okay, so far we've been talking about keyword searches and this sort of filtering according to topics. But there's way more to do in search. So on these slides, you don't just see words, you also see boxes and arrows. What is causing what? it's the microbe diversity, for example, that is causing more soil organic matter, for example. And you find this kind of language in the literature all the time. Deforestation in many countries of South Asia has led to soil erosion and flooding. So that's a direct causal statement. And this is a pretty basic thing that I don't think should surprise anyone. But there are many such statements throughout the literature. And here's a similar way. So you can see, even though the language is different, it's expressing much the same idea: soil erosion triggered by deforestation. So we know there's some causal element. So we have tools that can extract these kind of relations, these kind of causal relations from text. And right now, the general purpose, but we hope to adapt them even better to the soil health literature so that we can get not just deforestation to soil erosion, but more advanced and pertinent kind of relations. But even with these simple relations, such as deforestation to soil erosion, we can sort of put these all together into a much larger causal web, and then you can search over it. So I don't want to know, just show me anything about erosion. I want to know, tell me all the influences, all the things that cause or prevent erosion in the context of soil health, so that you're not getting skin erosion and things like that you would get in a normal Google search. Does that make sense? And we can even control the number of hops, so that if you want to find out the distal causes, you can do that too. And this tool already exists, as I said, in the general form. And so I was able to create, in a couple of minutes, this web of causes of erosion, things that prevent erosion, and some other pieces of the sort of causal puzzle. Now, the most striking thing to me about this is that you can look at any one of those arrows and see immediately the sentence that it came from. You can link to that document and go straight to it and read the whole document yourself. You can expand this, what are all the causes of drought, for example. I mean, that's not much of a mystery, but you can expand on this, and the most striking thing of all is this didn't come from the soil health literature. These papers are all in the children's health literature. So the good thing about this is you don't have to read the children's health literature to find out all these sort of distally related things to your work. The beauty of these machine reading algorithms is they can read many thousands of papers. They can read a paper every 4 seconds. And that's much faster than any of us, even if it's not as good at reading. So thank you very much. And I'm happy to answer any questions you have. Oh, thanks.